Hi and welcome to video 4 for section 8.3. This will be the last video for this section. In this section, the first thing we're going to look at is what's known as DeMoivres Theorem. And we use this when we're taking a complex number to a power greater than 1. So, for example, if we have that if z is in polar form, if our complex number is in polar form, r cosine theta plus I sine of theta, then z to the n power, when n is an integer, so then when n is an integer, z to the n power is r to the n power cosine of n times theta plus I sine of n times theta. So pretty straightforward, but pretty powerful theorem here. So as an example, let's say we have the following. We want to find 1/2 plus 1/2 I to the 10th power. So you could sit here and try to FOIL this thing out, and I've seen people do it on final exams because they don't memorize DeMoivres Theorem, and they have no choice but to try to multiply this thing out over and over and over. Very unlikely you're going to get to the very end without making a mistake at some point, whereas with DeMoivres Theorem it's pretty straightforward. The first thing, though, is you'll notice this is our complex number, but what? It's not in polar form. So we need to convert it to polar form to begin with. So if we do that, we get what? Our r squared is the square, well, r is the square root of a squared plus b squared. So a is 1/2, that squared is 1/4. And then 1/2 squared again is 1/4. So that's square root of 1/2, which is 1 over square root of 2, which is the square root of 2 over 2. So that would be our value for r. Our theta is what? It's tangent of 1/2 divided by 1/2, which is tangent of 1, which is what? So that would be either pi over 4 or 5 pi over 4. But where does this point lie? 1/2 positive, 1/2 up, that's in quadrant 1. So we want theta is pi over 4. So I can rewrite our original as the following in polar form. I want square root of 2 over 2 cosine of pi over 4 plus I sine of pi over 4, and I want this whole thing taken to the 10th power. I'm going to erase DeMoivres Theorem here. So then we get what? By DeMoivres Theorem we get r, which is square root of 2 over 2 to the 10th power cosine of n, which is 10 times pi over 4, plus I sine of 10 times pi over 4. Now when I simplify this first one, I get 2 to the 5th power over 2 to the 10th. So if I just bring this 10, this square root of 2 in exponent form is like 2 to the 1/2 power. So 1/2 times 10 is 5. So I get 2 to the 5th power in my numerator. And then 2 to the 10th in the denominator. When I multiply 10 times 4, I get 2 in the denominator, 5 in the numerator, 2 in the denominator. So cosine of 5 pi over 2 plus I sine, it ends up the same thing, 5 pi over 2. So that's our original taken to the 10th power, gives us this value here. So that's the application of DeMoivres theorem. The last thing we'll look at in section 8.4 is the nth roots of complex numbers. So we have the following. By definition, if z is equal to r cosine of theta plus I sine of theta, and n is a positive number, then z has the n distinct nth roots given by the following. So we use what looks like a W, it's an omega sign, so omega k is equal to r to the 1 over n cosine of theta plus 2k pi over n plus I sine of theta plus 2k pi over n. And this is for our values of k is equal to 0, 1, 2, etc., all the way up to n minus 1. So we'll look at an example. It'll make it a little more, hopefully, a little more clear as to what's going on there if we're talking about the nth roots. So let's look at an example. We have the following. Find the 3 cube roots of the following. Z is equal to 2 plus 2i. So the polar form for this, I won't go through the calculations again, but the polar form would be 2 square root of 2 times cosine of 45 plus I sine of 45. So in this case, I'm using my degree measure instead of the radian measure. That way when I have to calculate the numbers later, it's a little bit easier to crunch the numbers. So therefore, our omega k is equal to our r value, 2 square root of 2. And because we're talking about the cube roots, the third root, this is all going to be to the 1 over 3 power. Then we have cosine. So our theta is 45, so we get 45 plus, in this case, because I'm talking about 2k pi, our 2 pi is 360 degrees. So 360 times k all over 2 plus I sine, the same thing, 45 plus 2 pi is 360 degrees, so 360k over 2. And again, I'm using the degree measures just so when I have to start calculating, I don't have to work with all the radian measures. I can just use degrees, divide them out, and figure out what the values are. This will be a calculator problem. So now so this is our omega k. Now we need to find the 3 cases. So we have what? It's for when k is 0, 1, 2, etc., all the way up to n minus 1. Well, our n in this case is 3. So 3 minus 1 is 2. So I'm going to want to do k is equal to 0, k is equal to 1, k is equal to 2. This will give me the 3 cube roots for this complex number. So this guy here, if we simplify it, this becomes just square root of 2. And so we can do this, convert the square root of 2 to an exponent, combine them, take them to the third power. Again, it's a radical problem. If you want to see how we have to do that, just ask me in class. In the interest of time, I won't do it here. But this guy here, the first piece would simplify into just square root of 2. So for k is 0, we get square root of 2. And then cosine, so 45 plus 360 is 405 divided by 2. No, I'm sorry, k is 0. So it's just 45 divided by 2. So we get cosine, divided by 3, sorry. Because we're dividing by n. So this should have been 3. So cosine of 45 plus 360k divided by n from our formula, so divided by 3. So go ahead and change those out. So this should be a 3, that should be a 3. Because of our formula, it's divisible by n. So now when k is 0, the 360 piece is gone, so we just have 45 divided by 3 is 15, plus I sine 45 divided by 3 again is 15. When k is equal to 1, so again, we still get square root of 2 in the front, but now we have k is 1, so this is 360. 360 plus 45 is 405. 405 divided by 3 is 135. So we end up cosine of 135 plus I sine of 135. And then k is equal to 2. Again, we have square root of 2. So if k is 2, this is 720. 360 times 2, 720, plus 45 is 765, divided by 3 gives us cosine of 225, plus I sine of 225. So if this was on an exam, that's pretty much about as far as you could go. If on your homeworks, if it's asking for like to decimal places or something, if you have to calculate them, what you're going to do is cosine of 15, do that on your calculator, and we're distributing this square root of 2 to both pieces. So square root of 2 times cosine of 15 gives you approximately 1.366. And then square root of 2 times sine of 15 gives you roughly 0.366, and then we have this I still left over. For the second piece, cosine of 135 times square root of 2 is -1, and square root of 2 times sine of 135 is +1. So we just get -1 plus I. And then lastly, cosine of 225 times square root of 2 on your calculator gives you -0.366. And minus sine of 225 times square root of 2 is -1.366 I. So that's it. That is the end of video 4. The big one is DeMoivres Theorem. Please make sure that's on your cheat sheet. Make sure you know how to apply it. Has to be to a polar number. Those are the ones you're generally going to see on the final exam. Not so much the cube roots. I have seen them in the past, so you do need to know how to do these as well from the formula. But the biggest one is DeMoivres Theorem, so please make sure you know that one. So that's the end of the video series for 8.3. We'll see you guys in the next video series.